Welcome to AP Chemistry at Hondiga High School. I'm Brian Brown, and today we'll be looking at the parts of Chapter 12 that you need to know for the new version of the AP test. You'll notice the readings for this assignment are all over the place because we're really looking at little snippets of what used to be the last section in Chapter 11, and now they moved it to Chapter 12 in the Brown-LeMay book. So we're looking at solids and modern material. Now, one of the first things you really should understand is the different ways of classifying solids. So we have four fundamental different types of classifications, and really being able to differentiate between them, understanding their properties and understanding their bonding is really what most of this chapter comes down to. Now, metallic solids would be when you just have a metal. So it's a metal or a mix of metals that are held together by metallic bonding, the electron C model. That's metallic solids. Properties of metallic solids tend to be all over the place, but in general they're stronger. But there are some metals like mercury which are actually a liquid at room temperature. But most of our solids um, our metallic substances are solids, so most of them have stronger bonding. So in general, this is a little bit stronger type of bonding, but it's not as predictably always stronger like ionic and network covalent. The next type would be our ionic solids. Remember, that's characterized by starting with a metal or ammonium with a nonmetal. We have cations and anions held together in a crystalline form usually, but there's other types of ionic solids as well, which we'll look at in a second. Ionic solids, by the way, tend to have very strong bonding. So they're very hard to break apart. So they're solids at room temperature with high melting points. And we'll also get into their properties when we look at them a little bit deeper. The next type of solid that you should understand is our molecular solids. Basically, these are our molecular compounds that are solids at room temperatures. We've got all nonmetals with no ammonium, and they're held together themselves by covalent bonding, but in between they're held together by weaker intermolecular forces like van der Waals forces. And then finally, we have covalent network. Now on the surface, since these are nonmetals, they would look like molecular solids, but they actually do a 3D network of covalent bonding. That means their in-between forces are very, very strong, just like inside a molecule, the covalent bonding is very strong. And that makes these things like ionic solids, things that have very high melting points. So our weakest in general would be our molecular solids. They tend to be all over the place, but in general, they're significantly weaker. They're softer type substances as solids, and their bonding in between is weaker than the other three. Metallic can be very strong, but that tends to be a little bit more variable. And then your ionic solids and covalent network solids are very high melting point, very strongly bonded substances. And this is a table that looks at the four different types, some examples of each. It looks briefly at their forces in between and their properties. You should have a good working understanding of the ideas on this table, and they also hit all the properties that you should understand here. Now, when you think of solids, you need to understand that in general, there's two classifications of solids. Most solids fall into the first group, which is crystalline. So the particles are held together in a very highly ordered arrangement, like you see in the iron pyrite here. And in crystalline solids, which, like I said, is what most solids adhere to, they have, because of their crystalline and ordered nature, very definite melting points. As you warm them up, they'll reach a temperature at which you can break the bonding in between, whether it's molecular intermolecular forces or electrostatic attractions between the ions and so forth. You can reach a temperature at which it melts, and it melts at a sharply defined melting point. And the reason is because at its particle level, it's very ordered and bonded together in a unique, I should say, a non-unique, very reproducible type of bonding in every direction. So at a very sharply defined temperature, you have enough energy for the particles to break away and overcome partially intermolecular forces and go from the solid to the liquid. So at the simplest level, they're also very ordered. And that simplest level would be called the unit cell. It's the smallest portion of the crystal that get reproduced to make the structure of the entire crystal. And there's fundamentally three different types of unit cells: the primitive cubic, the body-centered cubic, and the face-centered. But we're not going to really get into it at that depth. You just need to understand at the simplest level, the unit cell, they're put together in a very ordered pattern. And the crystal lattice is that unit cell getting replicated over and over again in a large geometric pattern in 3D to give us our overall crystal. So most solids actually form like this. They have a very patterned unit cell that gets repeated to form the crystal lattice. Now, the other type of solid is the amorphous solid. And more substances are crystalline than amorphous. But in an amorphous solid, since there's no particular order to the arrangement, so it has a varied type of bonding within it, and the distances between the centers that are being attracted to each other and being held together in the solid are less ordered than in a crystalline substance. So consequently, they slowly start to melt by part. So they appear to soften over time. They have a melting range rather than a melting point. So they gradually melt over a range as different parts of the solid are turning into liquids, and the overall substance is becoming less solid-like and more solid-like until eventually you'd say, well, it's not a solid at all, it's a liquid. So it has a non-ordered arrangement, unlike crystals, and therefore it has a melting uh, range, not a melting point. Now, our first type of solid we're going to look at is a metallic solid. Now, metallic solids are not covalently bonded together. The attractions between them are too strong to be normal van der Waals intermolecular forces, so there must be some other type of bonding at play that we haven't really talked about, and that's the metallic bond. The metallic bonding is often referred to as the electron C model because the theory is basically that metals, which are inherently unstable, they have valence electrons that they would like to get rid of to become more stable, but no other metal around them, which is exactly like it, will take those electrons. So what they do is they give up their valence electrons and they become delocalized throughout the structure. So the valence electrons become mobile and delocalized, and that's why metals are inherently good conductors of electricity, because electricity is a movement of charge, and electrons can flow very well through the molecular or the metallic structure of our solid. Because of the fluid nature of the bonding that then exists because of the movements of the electrons, the cations, while they aren't really mobile, have the ability to be deformed and pushed around. So they're malleable. They tend to be soft rather than hard in many cases. And as a malleable substance, you can hit it with a hammer and they shift around because of the fluid nature of the attractions of those moving electrons. So what holds it together is an electrostatic attraction between the cations and the moving electrons, which makes it a mobile or moving type of bonding situation. So that makes them very, very, very malleable. And like I said, in general, they tend to be softer than ionic substances. But they're excellent conductors due to the delocalized nature of those valence electrons moving throughout the solid. Now, one particular type of solid that AP has included under the heading of metallic solids is the concept of alloys. An alloy is a material that contains more than one element, at least one of them. It must be a metal, but it's often mixes of metals. And it has properties that are similar to the metal that's in it, but not the same, because blending in other substances is going to change our properties. And alloys are very common in many aspects of everyday life. We can take a metal that is maybe very useful and strong, but we can even make it even more strong, or we can make it resistant to corrosion, or we can change to certain degrees its conductivity or its melting point, and so forth by blending other substances with it. Now, the two types of alloys that AP has said that they want you to have a fundamental understanding of are interstitial and substitutional. The interstitial alloy is the one that's on the right here. And interstitial means between states. So when you put small non-metal atoms or potentially metal atoms in between the larger metal atoms, like in the case with steel, they're putting small amounts of carbon in between the iron. And what this does, because of the increased bonding that now exists because of those carbon atoms sticking to the bonding, it makes it more rigid and less malleable, which makes the steel stronger, so to speak, than pure steel is. And it then ends up changing the bonding fundamentally just a little bit. So the properties of steel are similar to, but different enough that it's useful to put that carbon in there to make steel. So we can strengthen and lower the malleability of the steel by blending it with carbon. The other type of alloy is substitutional. Literally, you're replacing a like-sized metal. So when similar size atoms replace other metals in a crystal lattice, like in the case of brass, we end up with a substitutional alloy. So interstitial is you're putting it in between, and that changes its properties to a small degree. And substitutional is when you substitute one type of metal for other types of atoms. The density is going to be between the two, and they also typically end up less malleable rather than more malleable than the original metal. So those are our fundamental types of alloys that you should understand that would fall under the heading of metallic bonding, really, and metallic solids. Now, ionic solids are something that we've spent a great deal of time talking about in first year chemistry and already in AP chemistry. In ionic solids, we have cations and anions that are oppositely charged, so we're looking at an electrostatic attraction between opposite charged particles that form these large 3D crystalline webs of bonding. And ionic bonding is a very, very strong type of bonding, and it's in three directions. So literally to bring them apart, we have to break the ionic bonds. And ionic bonding is a strong type of bonding, so these things have very high melting and boiling points. And they're also very, very rigid, but brittle, which we'll look at in a second. And remember, what governs the strength of this bonding, so how high is your melting point, is Coulomb's law, the charge differences and the size of the ions. So larger charge differences lead to stronger lattice energies, and when the charge is the same, smaller ion size brings the charge centers closer together, which strengthens the bonding and makes a higher lattice energy. Now, when you look at a particle level about what's happening, it should make sense because it's a strong 3D web of bonding. It's a strong type of bonding, so ionic substances are very hard. But if you also think about it, if you hit a plane, and you can see this on the right side here, if you hit a plane of ions hard enough that you shift them over one space, you no longer have positive next to negative. You have positive next to positive and negative next to negative. And on a particle level, they start to repel each other. So when the ions get displaced partially, they repel, and therefore they'll jump apart. So while they're very hard, they're also very brittle. They're also, because of the strong bonding and the lack of movement of charge throughout the structure, they're poor conductors of electricity, and that's because the fixed ions don't carry a charge as a solid. Now remember, if we dissolve this in water, now we have moving charges, or if we melt it as a liquid, we have moving charges. So ionic solids are electrolytes. In their aqueous or in their molten state, they do carry a charge, or they are conductors. Now the next type of compound or solid is our molecular solid. And remember, our molecular solids are our nonmetals, covalently bonded together, so forming strong covalent bonds within the molecule, but weaker van der Waals or London hydrogen bonding and dipole-dipole forces in between. Because of the weaker intermolecular forces, these things tend to be softer and have lower melting points than all of the other types of molecular solids that we're looking at here. And examples would be CO2 and H2O. And remember, you can have hydrogen bonding, which is a little bit stronger type of van der Waals forces. You can have dipole-dipoles between polar molecules, and you can have relatively weak London forces. In every case, these are significantly weaker than ionic bonding or ion dipoles or covalent bonding or metallic bonding. So these tend to be much softer and have much lower melting points. Now, the last type of solid we're going to look at is the covalent network solid. Now, covalent network solids are like ionic bonding in that they're a strong 3D arrangement of atoms covalently bonded together. So unlike units that are covalently bonded and then in between those units, molecules, you have weaker intermolecular forces, here we have a covalent network in every direction of these stronger covalent bonds. So diamond would be a good example of that. That's the substance you see here on the left. Each carbon atom is covalently bonded to all four other carbon atoms around it in a very strong covalent network. And this, therefore, is very hard and has a very high melting point. Now, a similar arrangement of pure carbon is the form of graphite. And in graphite, you also have a 3D covalent bonding happening. But in this case, it's slightly different. You have plates, basically, of covalently bonded. And this is similar to, like we talked about in SO3 with resonance between the sulfur and oxygen. What we have here is delocalized pi bonding that's in resonance throughout this entire structure. And therefore, the entire plate is covalently bonded together. three delocalized pi bonding with sigma bonds in between, and that's a very strong covalent arrangement. So covalent bonds are stronger and harder to break, so the plates themselves are very hard to break. But what's unique about graphite in this case is the plates themselves in between are held together by weaker intermolecular forces, so they slide past each other much more easily. And because of the moving nature of the delocalized electrons, graphite is actually a decent conductor of electrons because the electrons can move throughout the sheet because of the delocalized nature. And because it's weaker bonding in between the two plates, they actually form relatively good lubricants. These sheets move against each other with very little friction. So if these are in between two moving particles, they help the two particles move against each other with less friction. So this is another example of a covalent network. And really, you have a very small sample of what you should know are covalent network type substances. So carbon, like in the form of graphite, and diamond would be a covalent network. Silicon and silicon dioxide. They tend to all have very hard surfaces with very high melting points. And really, those are the only ones you should know. Carbon in its diamond and graphite form, silicon and silicon dioxide. While your book mentions a few other, those are much less likely to ever be talked about. So really, if you see you've got carbon, silicon, or silicon dioxide, you just need to know its covalent network. And it's not a atomic substance or a molecular substance. It is a very strong type of bonding with a very high melting point in the covalent network. Now, the last thing that we're going to get into gets into a little bit of molecular orbital theory. In order to understand conductors, insulators, and semiconductors, which AP has also said now should be a part of the curriculum as modern materials that are important in our everyday life. So you need to have basically just a really cursory understanding of what's happening here related to molecular bonding theory to really understand conductors, insulated, and semiconductors and how they work. So fundamentally, you need to understand that solids have two bands of permitted energy levels for their electrons, the valence band and the conduction band. Now, the conduction band is at slightly higher energy, and when electrons move to the conduction band, then they will conduct electricity. So any type of metal, we say they are good conductors. So what happens in metals is the conduction band and the valence band are relatively close together. So they conduct very, very easily. So electrons are in the valence band and must absorb energy to move to the conduction band in order for conduction to occur. So really our different types of substances, conductors, insulators, and semiconductors, are about the differences in energy of those two bands. And what has to happen to conduct, remember, is our electron has to move from the lower energy to the higher energy band, and therefore it's free to now move and conduct electricity. And that takes a little bit of energy. Now, in a conductor, there's little or no gap between those bands, so it really takes very, very, very little energy for the electrons to move from the valence band to the conduction band and for it to conduct electricity. And this is what metals would look like. Their conduction band and their valence band are very, very close together. Now, in an insulator, there is a large gap between the two, so it's very unlikely that the electrons are going to absorb enough energy to jump from the valence to conductor. And this is really what nonmetals do. So nonmetals have a large gap between the valence band and the conduction band. And in a semiconductor, we have substances like silicon that have a small enough gap that with a little bit of energy in the form of heat, the electrons can bridge the difference between the two and conduct. So in a normal situation, they wouldn't conduct, but with just a little bit of added energy, they can move from the valence to the conduction band. And that's because they're not too close together and they're not too far apart. And this is unique to some substances in the periodic table, like silicon. Now, one of the things that they have mentioned you should understand is we can take semiconductors and through the process of doping, we can add other atoms to the semiconductor to actually increase its conductivity in places. And this is really important to electrical circuits and transistors and so forth. Now, there's two different types of ways to dope. And I'm going to hit this at a very, very quick level. So I'm going to mention in a minute, there's a short video I want you to watch that really makes this a ton easier to understand because they have an awesome animation to it. So one type of semiconductor, one type of doping is the N-type semiconductor. And what we're doing here is we're adding atoms with more valence electrons than silicon, like phosphorus. And when we add those into the lattice, the extra negative charge um, electrons allow the conduction band to more easily be bridged from the valence band because of those moving charges basically throughout. So it's conduction through moving negative charges when we dope the silicon with something like phosphorus with extra electrons. So if we put something with more valence electrons, then we get one type of doping. That must mean we must put less electrons, substances in like boron or aluminum, and we get a different type of movement. And this is one where it really makes sense to watch the movie. So what we've got are positive moving charges in our p-type conductor. So what I strongly recommend you do is watch the movie that's on the PowerSchool Learning page called How Does a Transistor Work? It really will take you through these two types of doping situations better.